Hi. Uh, Hi. The agenda of the today video is to cover the Coulomb's law of your electric charges and field chapter and try to finish this law within a 20 minutes of time so that you can solve the questions, whatever the question asked in JEE or NEET by watching this video. So let's begin with as you know, if you have a ebonite rod, right, and if you're supposed to rub this ebonite rod with the help of wool, then this rod becomes positively charged. Whereas let's say if you have a glass rod and if you're supposed to try to rub this rod by the with the help of silk cloth, then this glass rod will becomes negatively charged, right? So basically we have the two charge in nature. One is called the positive charge, whereas the second type is called the negative charge, right? So that this name positive charge or negative charge is given by the one of the famous scientists from America, known the name of that scientist is Benjamin Franklin in 1750. So in 1750 he gave these two names. One is called positive charge and second one is called negative charge, by observing these two experiment, right? So also let's say if you have any material and the net charge of on that material is, let's say, zero, then you can say that that material is electrically neutral. So you can say that that material is electrically neutral if the net charge on that material is zero, right? So other properties of charges is, let's say if you have a two charge and the both charge of the same nature, that means let's say the both charge either is positive or a negative, then if you're supposed to place both charges at a particular or distance, let's say r, then both charges try to repel each other. Similarly, let's say both having the negative charges, the same phenomena will occur, like both try to repel each other. Let's say one is positive and one is negative, then both try to attract each other. So this is the one of the nature of the charges, where that the charges are repel each other when both are positive or negative, or charges are attract each other when one is positive or one is negative. That is called unlike charges. Some of the basic properties of electric charges that I mentioned here is, one is the charge is quantized. What does it mean? That mean is, let's say you have a charge on any body, right? So you can write the number of charges or total charges is integral multiple of fundamental unit of electric charge. What does it mean is, let's say you have a body having containing let's say n1 electron and also containing n2 proton. So you can easily write the total charges on that body is n1 times of electron, right, plus n2 times of proton. Because electron is having a negative charges, so you can write minus n1 of e plus n2 of e. These n1 n2 is of course is a integer value, right? The second properties of charges here is the charge is conserved, right? So that means the total charge of any isolated system remains constant. Nobody can create a charges nor destroy a charges. So this charge is always be a conserved quantity. The third property is charge is additive. The means of charge is additive is, let's say you have a body having charges of q1, q2, q3 and q1 amount of charges. You can write the total charges is nothing but summation of all the charges. Let's say if any charges is negative, you can write q1 minus q2 plus q3 and so on, right? So because charge is a scalar quantity, you can easily write with the sign. Now, the fourth property is charge is invariant. Let's say you have a body and that body contains a charges, and let's say that body either on rest or in motion. So the numerical value of that charge will not changes depending upon the state of that body. So the numerical value of the charge on and let's say isolated system or object is independent of its state or motion. So these are the four basic properties of electric charges. Moving on, I have here mentioned a small thing. Let's say you have a two body, one having a one having a TQ charges, other body having a, let's say, minus 4Q charges, and let's say the both body comes contact to each other for a particular instant, and then again separated by with a particular distance, let's say r. So now, of course, because due to the interaction between these two body for a particular time or instant of time, now the new charges becomes on the both body is nothing but q1 must be equal to q2, that is the average charges of individual body. This is 2q plus of minus 4q divided by 2. This is the average value, right? So you can easily calculate it. Q1 is equal to q2 is nothing but minus 2q by 2, that becomes minus 2. So now this q1 is equal to minus q1, this q2 is equal to minus q. So you can easily, now you have a both body having the same charge of magnitude minus q. Now, the next important topic of today's agenda is Coulomb's law. As you know, the Coulomb's law is basically comes in a picture due to his experiment. So what he did is basically he placed the two charges in a space. So one charge is at a particular distance, position vector of r1, the other charges at a position vector of r2. So the distance between these two charges is nothing but r2 minus r1, right? So this is the distance between the two charges. Now, due to as I had mentioned, the positive, the like charges or unlike charges try to either attract each other or repel each other. So what he observed that the force of attraction between these two or force of repulsion between these two charges is nothing but the directly proportional to the product of these two charges and inversely proportional to the square of the distance between these two charges. So he gave a law that is nothing but force is equal to k times q1 q2 by mod of r12 to the whole square. And you can see here this proportionality constant k is also depending on the media where these two charges are placed. Here you can assume that these two charges are placed in a vacuum or air, right? If you place in a vacuum or air, so k is nothing but 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught, and this epsilon naught is nothing but permittivity of the free space or vacuum. And this k value comes out to be 9 into 10 to the power of 9 newton meters square per coulomb square, and this epsilon value is nothing but 8.85 into 10 to the power of minus 12 coulomb square per newton per meter square for vacuum or air. Let's say if you want to place these two charges other than vacuum, then you can write permittivity is nothing but small k times epsilon naught, and this k is nothing but the dielectric constant of that medium, right? Moving on, because as you know, the force is nothing but the vector quantity, so you should write force is equal to some magnitude of force into unit normal vector. So I am writing here is force is nothing but the magnitude of force times unit normal vector. And you easily know how to calculate the unit vector is nothing but the position. Let's say for this case is position vector you have given, so r1c2 mod of r1c2, right? If you club this value to here, so you can write force is nothing but magnitude value is nothing but k times q1 q2 by magnitude of r12, right? R12 multiply by normal vector is nothing but r12 divided by mod of r12. So this force comes out to be k q1 q2 divided by r1 to the power of 3 r of 12, right? So this is the force in a vector form. Right. So there is one more principle of superposition of charges that is used, because let's say you have a pair of charges and also you have a more than pair of charges. So what happened on individual charges? So this principle of superposition of charges says, let's say the net force on any charge is a just simple of vector sum of forces exerted on it by all the other charges, taking one charge at a time. So the simple meaning is, let's say you have three charges, you want to calculate the force on, let's say, charge 1, then you can easily calculate force on charge 1 by charge 2 at one time. In the second time again you calculate the force on charge 1 by the impact of charge 2 or charge 3. Then the total forces on that particular or selected charge is nothing but the vector sum of force due to charge 1 plus force due to charge 2 or charge 3, and so on, right? So now, as I mentioned, the theory part, the important part of the today agenda is how we can use this Coulomb's law into solving of number of problems, right? So you should follow the two general step here. The first step is, first you calculate the magnitude of forces, that is nothing but k product of charges by the square of separation distance between these two charges, right? So first calculate the magnitude of forces using Coulomb's law, ignoring the signs, just ignore the signs for a moment of time. Next step is, you know, the positive charges is repel and the negative charges attract. Depending upon this nature, you just draw a vector diagram on the selected charge, right? So these things I will use. I am trying to demonstrate some examples here where you can understand what I am trying to say. So let's say you have a two charges there, the Q and Q, both are the same magnitude, Q. The green color is my interest point, right, where I want to calculate the force. So the green color where I want to calculate the force. So for your convenience, I mention here is one is charge Q, sorry, and two is charge green Q, right? So you can say, okay, I want to calculate the force on two that will impacted or repulsion by the charge one. So you can write here is equal to product of charges, that is q, that is q square divided by distance by square. You got the magnitude. Now the next part, what is the direction? So direction is, you can draw a vector by just looking the charge of nature of charge. So here this one charge is positive and two is also positive, and your aim is to calculate the force on charge 2. So the charge 1 is positive, so force of repulsion, that arrow goes like that, right? So in the x direction, you can say this is the I unit vector, this is your force. Let's say for this case, again my interest point is this green color. So the magnitude of forces is nothing but again this k q square. I am ignoring the sign here, by r square. Now you look the charges. So let's say this is the charge 1 and this is the charge 2. You want to calculate the force on 2 by 1, force on charge 2 by 1. Now looking the sign, the charge 1 is negative charge and try to this attract, so it goes a negative direction, so minus I, right? So these are some examples where you can understand how you draw vectors on individual forces, right? Let's say you have a bunch of questions you find in NCRT books and JEE questions, right? So let's say I just draw some attention on those type of questions. Here the q positive q amount of charges are placed on the triangle, whereas the q naught, again the same nature of charges, positive q naught is placed at the center of the equilateral angle of the triangle, right? So let's say you have given a theta here. So the first step is I just draw, this is charge 1, this is charge 2, this is charge 3, right? So this q, due to this charge 1, both are positive, so vector diagram goes like that. I just write f1, right? Similarly, due to this charge 2, this force goes like that. This is F2. Charge 3, the force goes like this. This is the procedure. You can draw forces, and you can see here, here F1 is equal to F2 is equal to F3. That is F. Why? Because these all distance, right? These all distance are same. This distance, let's say A1, so this must be equal to A1, and this must be equal to A1, right? So this F1 is equal to, and also the charge is also same. So K Q naught, Q naught, K times divided by this A1 chi square. You can F1 is equal to F2 is equal to F3 is equal to F. And now you know the direction of force. You can easily calculate the F net. For this case, you can see here, one is force F3 is going down, one is F2 here, F3 here. So this horizontal component becomes theta. This theta is cancelled out, only you got a vertical component of forces, right? So your net force, you can F net is nothing but 2f of sine theta minus F3, and F3 is also F. This is your final answer. Let's say you have a circle and the charges are places like this. So the q amount of charges placed at a radius r, and the q naught is placed at the center of the circle. Again, you draw, let's say for nomenclature, I write 1, 2, 3, and 4, right? So on this center, by this charge q1, this is force F1. This charge q2, this is force F2. This is charge 3, this is repulsion of F3, and this is charge 4 due to repulsion of F4. You can see the radius is same and the charges are same, so F1 is equal to F2 is equal to F3 is equal to F4. Due to this direction, right, this force cancel out of this and this force cancel out of this, so you got F net is equal to 0, right? So net force on the center of the circle is 0. Let's say again you have a charges on a square of side A, and your interest point on this blue charges. So you can draw, uh, let's say I just nomenclature 1, 2, 3, right? And you can draw here due to this charge 2, it goes like that. F2, charge 3 goes like this. F3, charge 1 goes like this. F1, right? So if this is a 45 degree, so again this is a 45 degree, and the F net will be, if you just calculate the F net value, so F net value will be this component resolve, this component resolve. So F naught is nothing but F2 plus F1 cos 45 degree plus F3 cos 45 degree, right? Now let's say the charges are uh, placed on a pendulum cases. Here you can see the two charges q and amount again q on a rod of length L, and the distance between these two charges is, let's say, d. And again, let's say you need to find out what is the value of these charges, and let's say tension if one is given. So the simple thing is you first draw, let's say, a free body diagram of any charges. So let's say this charge is having the mass m also. So you can draw here the mg force coming down. If this is theta, this is also theta. So this is tension, right? You can draw vertical lines. So you get here is t sine theta, right? Because if this is theta, no, sorry, this is theta, right? So you get t cos theta, right? And now because this is the positive charges, this is the positive charges, you got one more force here, that is electric force, Coulomb force, that is F, right? So now, and also this is t sine theta. You can, now you have a equation, that is equation of equilibrium, where the x force must be balanced by x dimension forces and y force must be balanced by y. So you can use the vector and balance the forces, and you can easily calculate the individual things, right? One more important questions generally asked, where you have a two positive charge q, right? And in middle of a small charges q of mass m is placed, and then he is supposed to give a small displacement x to these charges, and then say what is the frequency of oscillation of this object, right? Omega, they want to ask. Again the same thing, because now you displace this charge by a small amount of x. Now this instant this charge is here, right? Sorry, this charge is here, right? So I just, this charge is here. Now let's say initially this total distance is, let's say, 2L, and at the center this distance is L, right? Let's say initially, after an instant of time you displace this charge as a particular distance x. So now this distance becomes L plus x, and this distance becomes L minus x, right? Again now you draw forces due to vector diagram, because this is a positive charges. So here you can feel, let's say this is the force 1, charge 1, or this is charge 2. So you can draw, this is F1 and this is F2. Now what happened here is, because your charge is displaced a small distance x, so the net force on that charge will be, if you write a magnitude terms, so F net is nothing but F1 minus F2, right? Now you look which one is higher in magnitude, right? So F1 is, so F1 is due to this left hand side charges is k q q divided by distance, and then distance is nothing but L plus X, right? This is F1. Similarly, you can write F2 is K Q divided by L minus X. Sorry, this is a whole square. Correct. By looking these two values, the K Q nominator value is same for the both cases, while the denominator value in the first case is L plus X, in the second case is L minus X. So for the denominator value for force 2 is less than the denominator value of force 1. That means force 2 is higher than force 1. So the net force in your magnitude terms, right, is nothing but F2 minus F1. That gives you a positive value, right? So this is the net force, and that must be equal to centripetal force, that is nothing but m omega square into displacement x, right? Here everything is given to you. You can easily calculate what is the omega value or time period of oscillation. This time period of oscillation you can calculate by using this formula: omega is equal to 2 pi by t. Moving on, sometimes you also find the question based on nullity, right? Nullity means, let's say you have a two charges. One charges is q and the second charges is proportional to 2 times, proportional to 3 times, proportional to n times, right? So here let's say you have a one charges is q, the other charge is proportional to 3 times, so it's 3q. And then they're supposed to put another charge q naught on a particular distance, let's say x, and then they ask what is the force value that becomes zero, exactly zero at this point. What is the distance of x at which the force value at this point becomes zero? What does it mean? That means that the forces due to this small charge that is acting like this direction, let's say this is F1, and forces due to this charged q3 is acting like this, must be what? Must be equal, right? Must be equal. So if these two forces becomes equal, then what is the value of x? This question is called nullity problem, right? So you can easily solve, because you want to find a x at the equilibrium position where these two forces must be equal. So you just write F1 is equal to F2, right? And then you can calculate F1 is nothing but k q naught divided by x, and this F2 is nothing but k q naught. Here is, you have a 3q, so 3q naught divided by this distance is now becomes L minus x, this is, sorry, x square, so this is x square, right? And then you can calculate what is the x value here. Keep in mind that for finding an nullity, you can use this formula always, right? Whether that is a proportional or not. So this kind of question is generally asked. You can use this formula to calculate any kind of question, right? Thanks a lot.